Institute for Responsible Carbon Removal at American University. As always, I'm your host, Will Burns. I am co-director of the Institute. As everyone in the carbon removal ecosystem knows, it's going to take a village to raise this sector, right? And that's true with allied climate intervention approaches, one of which we'll hear about today. And an important member of that village is the philanthropic community, right? And philanthropy has various roles to play. In some cases, some of the research that we're looking at and some of the other efforts to enable carbon removal and other climate interventions requires very large amounts of funding, and some philanthropies fulfill that role. However, there's also an important role for seeding specific aspects of carbon removal, as well as providing foundational research. And I thought it would be interesting to highlight the role of one of those philanthropies, as well as a case study of a recipient of one of those grants to demonstrate how this works, and also to introduce a potential source of seed funding for those of you that work in this sector. So I'm very pleased today to have two guests. Peter Jenkins, who serves as the fund manager for the philanthropy that we're going to focus on today, the Climate Intervention Environmental Impact Fund, or CIEIF, as well as Dr. Maarten van Herpen, who is a principal scientist for Acacia Impact Innovation BV, a recipient of a CF grant, and who focuses on an allied intervention to carbon removal, which is atmospheric methane removal. So we will proceed today as we always do. We'll have initial interventions starting with Peter to provide an overview of how CF works, and then we will proceed to a presentation by Dr. Van Herpen, which will tell us a bit more about their specific approach in terms of methane removal. And then we'll move to a couple of seating questions for myself, and then to audience questions. So in that latter context, I encourage audience members to begin to seed the question and answer box when questions arise, so I have some sense of how much time to allocate for that at the end. And so with that, I will turn over the lectern to Peter Jenkins. Peter?
Yeah, thanks, Will. Thanks so much for hosting this session, and greetings to everybody out there in the audience. I'm here in snowy Bethesda, Maryland, and I thought I'd do a quick intro about me because I'm the manager of this fund, the Climate Intervention Environmental Impact Fund, and that is that for about 40 years I've had a career as a attorney and policy advocate, mostly in DC, several years with government, but mostly with NGOs such as Defenders of Wildlife, Conservation International, and a few other NGOs. Right now, I'm at a group called Public Employees for Environmental Responsibility, working half-time there, peer. But in all that work, doing environmental law and policy, I have managed to develop a strong background in environmental impact assessment and working with stakeholders and the law around and the sort of the practice around environmental impact assessment. Well, it happened in 2020 that for about 3 years, I began to serve as the chair of the advisory panel for a small NGO called Methane Action. And Methane Action was focused on the technology of removing methane from the atmosphere. And in that process, kind of got my hands really dirty and fully engaged in this whole world of CO2 and methane removal. And that group, by the way, Methane Action, then merged in 2023 with Spark Climate Solutions. And it was then that we started this fund, CIEIF, to meet what was perceived as a key need in the field, which was that there were investigators proposing field tests. Some had proposed field tests in other contexts, which really hadn't had adequate EIA work, environmental impact assessment work done, or stakeholder engagement. And you're probably aware of some of those situations where projects got stymied or were not allowed to go ahead because of basically that failure to really engage the stakeholders or to do adequate EIA work. So we started this fund with the idea of giving grants to help investigators do that in this gap that was perceived. And in the last 3 years, we've now given about 10 grants so far, totaling altogether about $500,000 in grants. But now we're up to the level of $75,000 flat per grant, and we give 3 grants per cycle, and 2 cycles per year is kind of the goal. So just so you know, our next deadline is March 15th, and all the info is on our website. I'll take you to our website in a minute. But next deadline is March 15th, and then next one after that will probably be about October 1st. And I should say that it's been exciting to do this work because it gives us a chance to, myself and my advisors, gives us a chance to engage with people like Maarten, who you're going to hear from shortly, as well as Will Burns, who is part of a team that's also a grantee called Global Ocean Health. And we may delve into that one a bit later. But it's been great to work with these investigators. So at this time, I'm going to take you to our website. If I can share the screen properly. Where's the website? Okay, share. Can you see the screen?
Yes.
Yes.
Great, great. Cool. And what I want to do is take you to the original page on the website. Well, actually, we can stay on this page for a minute. This lists our current grants, and I'm not going to spend time on each one, but you can see we have a number of cool different projects ranging from Arctic ice reflection to aquatic methane to CO2 removal by enhanced rock weathering, and a whole array of different technologies have been funded. And our grants go worldwide, I should say. We've got a grant in Pakistan, a grant in several in the Netherlands, one in Germany. So at this point, I'm going to go over to the key page on our website, which is what we do. So this is at CIEIF.org and what we do. And it's important for anybody interested in applying for a grant to read this one carefully because it sort of describes the range of what we do and what we don't do. And what we don't do is give basic research or implementation funding. Really, our grants are targeted to those who need funds for EIA work or stakeholder outreach work or impact modeling. Those are our areas. And in terms of the climate interventions that we fund, they include sort of the things that are listed on that page. I'm not going to read them all, but we do exclude DAC because of other funding for DAC, we think, as well as stratospheric or higher solar radiation management. We don't get into that for sort of philosophical reasons at this point. But everything else is fair game, again, worldwide. And in terms of the grantees, it can be entrepreneurs like Maarten, or can be academic institutions or NGOs. We have funded in all those areas. So now I want to go back to the website and look at the other key page. And by the way, I should say that again, that our grants tend to be supplemental to existing grants. Most of our grantees already have other implementation funding. I want to go to the grants page. We talked about the current grants and past grants. Now we're going to click on the grant guidelines page, and that's the nuts and bolts of if you want to apply for a grant from us. You got to demonstrate how you're going to usefully use the $75,000, and that of course includes budgets and so on. But there are 10 items on this page. Not going to go through them all, but there's no, by the way, there's no form either. You just have to supply the 10 answers. But I'm going to emphasize three main things that after 4 rounds of doing these grants, we've realized that we tend to focus on. The three emphases are on the qualifications of the investigators. That is crucial. And then the science, of course, behind the technology that's proposed. We need to make sure that these innovations are at least well supported in science and feasible. And then the scalability is the third thing. Is it just a local solution to a problem, or does this technology have the potential to scale to a climate relevant scale? Of course, that's what we are really hoping for, is the golden fleece, is climate relevant scale to make a difference in the climate. So the last page of these that I'll go to now is this one about us. It just to mention the fact that it's got a bit more on me, but our two advisors, Renaud Directeur is our science advisor in France. Really, he's got his hands on, or he's got a great handle on the full scope of climate interventions, ranging all across the board. And then John Fitzgerald, who, like me, is a DC legal person, but John is our legal advisor. So we have some good scope of coverage in our team. And I'll just try to wrap up my session before turning it over to Maarten shortly by saying that we encourage anybody out there who's got a strong team and a good idea to apply by March 15th. Feel free to be in touch through our website. It's got an email that you can email to us. And if you have questions, in preparing a proposal, we're happy to provide advice before people submit. Again, it's worldwide coverage, and all entities are, except not individuals, but they have to be, solid entities to apply. And just by way of background, I counted them up. Of the 9 grants on our webpage now, 7 were to private entrepreneurs and 2 were to NGOs. So that's it for now. I'm going to stop my sharing, and I'm going to look forward to the Q&A session later. And thanks. Let's see. Did I stop the sharing? Oh, stop share. Okay. All right. I think we stopped the sharing. And now I get the pleasure of introducing Maarten van Herpen with Acacia Innovation, who is one of our grantees. I've worked with Maarten for several years in the methane world, methane removal world. So really looking forward to hearing what Maarten has to say. Okay.
Well, thank you, Peter. And
Sure.
so Will also asked me to briefly introduce myself. So my name is Maarten van Herpen. My background is I've got a PhD in physics and a master in business innovation. I worked for a long time at a large multinational company where I was inventor, and then later also was leading innovation in the company. And especially I also led innovation for healthcare innovation in Africa to try and create medical innovations for low resource settings. But about 8 years ago, that's when I started to work on methane removal. And that's also the topic that I talk about today. I'll share my screen. I think it should be there now, Peter. And so for about 8 years already, I'm working on this topic. For example, Professor Matthew Johnson has been with me for all these 8 years now, working on this in this field. And today I'll talk a bit about atmospheric methane removal. And as Will already pointed out, it's a bit different from CO2 capture. That is normally what you talk about in this on this platform. So in my presentation, I will first talk a bit about methane itself as a greenhouse gas and why it's different from CO2, and about that new field of atmospheric methane removal. And then I'll go into the topic of the CIEIF project that we're starting, and that's on plume-based atmospheric methane removal. And it will become clear in the presentation what we mean with that. So I'm working on this with Matt Johnson and also with Professor Earl Goodheer from High-Tech Excel. Now, first about methane. It's very different from CO2. So one of the big differences with CO2 is that methane is much more potent as a greenhouse gas. Compared to CO2, it's, for example, 87 times as powerful over 20 years time scale. But the other big difference is that methane also has a much shorter lifetime of about a decade in the atmosphere. So it's doing its impact in a relatively short time. And now, the other big difference with CO2 is that the typical ways how you would capture CO2, they don't really work for methane. It's very inert, so it makes that things like CO2 capture difficult. So, for example, it does not stick very well to surfaces. It also reacts super slowly, so it's like a noble gas almost in how it reacts, and it doesn't really dissolve easily in water. And these are all strategies that you would use for CO2 capture, but it doesn't work for methane. But it does have an Achilles heel. It's because it only has this decade lifetime in the atmosphere, and that's because it's easily destroyed in the atmosphere by radical chemistry, in a reaction with things called hydroxyl, OH, and chlorine atoms. And that's the main way how methane gets removed in on the planet. The other way how it's different from CO2 is in its sources. So I explained in this figure, you can see that the main sink is the destruction in the atmosphere, but the sources of methane, half of it is actually coming from nature, roughly. And the big driver there are wetlands. And the other half, caused by humans, is mainly fossil fuel and agriculture. And especially agriculture is a very large methane emission source. And most notable here are cows as the main source. Now, next thing that's important about methane is that it's one of the few things where you could take action to limit the warming on the shorter term. That's because it stays in the air only for those 10 years. It means that the warming that methane has today is caused by emissions that happened in the past 10 years. That for today, that means half a degree of warming that is currently caused by methane, about a third of global warming. And if you look at these IPCC scenarios here, then it is actually still possible to stay below that limit of 2 degrees, but it requires tremendous cuts in methane emissions. From 400 to 200 million ton of methane emissions, it should be the cut that needs to be made urgently if you want to achieve that. And in theory, it's possible to do that. However, the reality is different. Methane emissions are going up, and we see record levels of methane in the air today. So it's not going in the direction where it should be going. The other thing that's important is climate tipping points that are being crossed as these temperatures are going up. And you've probably heard about coral reef die-off. That's already happening at the moment. And there are all these other tipping points that are being triggered as the planet is warming. And some of these are also causing additional methane emissions. For example, the melting and the thawing in the Arctic, and the sea level rise, the increase of wetlands. These are reasons why more methane is being emitted. And that creates a feedback loop with methane causing warming, and that causes more methane emissions to happen. All of this causes also a lot of damage to the economy. And an interesting paper that came out this year in Science, okay, of course, in the last few months at least, that's last year, is where they calculated the economic impact of methane emissions. And with half of America currently suffering from a snowstorm, I think it's clear how very bad weather, how extreme weather can have damage for the economy. These researchers studied that same 200 million ton of methane emission reduction from that previous slide that I showed. They see that resulted in 0.2 degrees temperature reduction on the planet. And that had its impact through less extreme weather and reducing the climate-related damage in markets. And they found 0.4% of GDP is what the value is. And then on top of that, there are all kinds of other benefits, such as, for example, ozone pollution that is associated with methane emissions. And ozone is very unhealthy and has bad effects also for agricultural yields. So the additional benefits are also there on top of it. And what they showed is that, therefore, it has big value in reducing methane emissions for economies. It pays itself back at least 6 times over. And the gains are so big that even individual countries, so for example, the USA, the emission of a ton of methane costs the economy $1,000. And that comes down to about $40 per ton CO2. And that is the value that it has to actually reduce these methane emissions. And then globally, it's around $200 per ton. So that's a lot of value in reducing these emissions. Now, next to those that need to reduce these emissions, there's now another field emerging, and that field is atmospheric methane removal that you could use to mitigate those emissions that cannot be mitigated otherwise, or those emissions that are coming from nature, and those are also going up. That can then help to reduce these climate risks and damage to the economy. The National Academies published a report last year on this new field, and they also showing different ways of how this could be done. For example, you could have a methane reactor, a reactor that you could place. A company called Ambient Carbon is putting these things next to cow barns now, and they take cow barn ventilation air and they send it through this reactor to destroy the methane in it. Other things that can be done is, for example, a surface treatment like titanium dioxide coated buildings. An ecosystem uptake where, for example, trees take up more methane and destroy it like that. But a big amount, a big potential is also in this atmospheric oxidation enhancement, where you're actually enhancing the sink in the main atmosphere. And that needs to be done through the dispensing of certain particles into the air. And this figure is in this report, but it doesn't have this part that we added ourselves, which is the plume-based reactor. So this is an intervention similar to this one on the right with atmospheric enhancement, but now it's only happening inside of the plume of, for example, a ship, and that restricts it to a certain location. Why is this needed? Is because most of the emissions, this graph here in the middle bottom shows the concentration at which methane is emitted to the air. While oil and gas kind of emissions are at a high concentration, they can be burned off with flares, for example. Most of the emissions are at a lower concentration, and it's at this concentration where it's really hard to mitigate the emissions in another way. And that's why this field especially needs to focus on these kind of emissions, but it is the majority of the methane emissions that are out there. So we did some study to see if, in theory, this could work, this idea. In our paper in Nature Communications, we did a science fiction experiment where we had chlorine being emitted from all over the oceans. So in the global model, we emitted lots of chlorine gas, and that would then destroy the methane. And what we saw is that the principle works. So in the methane burden in the air, we could bring it down and cut it in half by emitting the chlorine. But one problem is it needs a lot of chlorine that needs to be emitted. But in principle, it's possible, but it probably has a big impact on the environment. So we also studied that, but I'll get to that. So one of the other things we found is if we zoom in on this initial part, is that small amounts of chlorine, as it is emitted, is actually increasing methane. So we had to overcome an initial burden of chlorine emissions before it started to work and methane started going down. The other adverse impacts that we looked at, the main adverse effect of this experiment was that these chlorine emissions led to an increase in acidity. And that's because Cl2, when it reacts with methane, it makes hydrochloric acid. And that increases the acidity of the atmosphere and the ocean if it deposits in there. The other impact we saw was a slowing down of the ozone layer recovery rate. And the reason for that is that methane is associated with ozone production. So if you cut methane in half, then there's less methane in the air to make ozone. And it's good for ozone pollution in cities, but it also means that ozone is not recovering as fast higher up in the stratosphere. And then let's go to the next slide, because what we are doing in our project, it's called the ISOMO project, is to try and find chemistry that we can use to address these high methane levels. So it's just like other researchers that are in the Amazon or in coral reefs, and they're looking for chemistry that you can use for medical applications. We look for chemistry that can actually help us to do something about methane in the atmosphere. And what we found is that that dust, as it travels from Africa across the ocean, is able to destroy methane as it crosses the oceans. And the mechanism that we propose for this is that as the dust is uplifted in Africa and it crosses the ocean, it descends and then enters the marine boundary layer. This is where sea spray is in the air, and that mix of dust and sea spray has a mechanism that we propose works like this. There is iron in the dust, and the iron can have two states, an iron 2 and an iron 3 state. And when it goes from 2 to 3, we call this oxidation. Then when you have an iron 3, then that binds with chlorine and makes something that we call an iron chloride, and that can photoreduce. When the sun shines on it, it photoreduces and goes back to this version 2. And then this oxidizes and it just keeps cycling around, and each time when it photoreduces, it produces a chlorine atom. And this is a mechanism that's well known from laboratory studies and other things. This chlorine atom then reacts with methane. It can also react with ozone and remove ozone pollution. It can react with all kinds of VOCs. And as it does this, it produces the hydrochloric acid that I mentioned before. But the difference with this dust is that it's being taken back up by the aerosol. So the aerosol is recycling the acids. It's a cycle there, and there's a cycle in the iron. So it's two catalytic cycles that together are destroying methane. So that's nice because the hydrochloric acid is not increased, so it's not creating extra acidity like we had with our other experiment. And when the chlorine destroys methane, it makes carbon monoxide as a temporary intermediate. Carbon monoxide is in the air for about a month or so. But what's nice is that this carbon monoxide, if it's made by chlorine destroying methane, it has a signature in its isotopes. We call it 13C depleted in CO. And that's what we started studying. What we did is we looked at these isotopes and we compared initially Barbados and Tenerife. In the 90s, a researcher called John Mack, he collected flasks of air and looked at the isotopic composition. And back then he already concluded that what he was seeing is big depletions happening in Barbados in these measurements compared to, for example, Tenerife. And he concluded that that must be due to methane destruction from chlorine, because that's the only way how we could explain that signature. And then what we did is we performed modeling to see if the dust could be, the mixing of the dust and the sea spray could explain what he saw at Barbados. And we were able to explain that. For example, here you then see a map with, so this is a yearly average showing the amount of depletion that you get in that signal, in that isotope, if you measure it there. And then the next thing we did with funding from Spark Climate Solutions is to now see if it also is the same today in today's world. And we do that by collecting flasks of air. So here at Tenerife and Cape Verde and Barbados and at the Amazon, we are collecting flasks of air and looking at the isotopic composition. And we get help from ships. The seafarers are helping us by filling flasks of air and bringing them back to our lab. And there we, for example, published a paper where a ship has crossed through this dusty region. And as it crosses through, we saw these highly unusual points. We call this then depleted points, which are signatures of that methane destruction happening. And they are then compared here with the normal data points, which are the other data points on this graph. So we're also seeing that it happens also today. But on our stations, we think we're seeing much less of this activity than there was in the 90s. But we're still analyzing that data. Now, some researchers have proposed to add this type of iron, this type of dust, to ship plumes to try and destroy methane in the plume of a ship. So this is a figure from this paper. And you see here a picture where they added these particles in the plume of a ship. And they also proposed other ways of dispensing these iron particles. And so we started looking at, is this feasible, this idea? So this was also done with the support from Spark Climate, where we did modeling to see how well does this idea work. What we found is that the removal of methane, we found the same effect that if you have a high intense emission of chlorine, that it works very well. So if you look in this total figure over here, what you see on the horizontal graph here is the NOx. You could think about this as the amount of air pollution. And on the vertical axis is how much chlorine is emitted or how much iron is added to the ship plume. And what we see is that if you are at a very high amount of iron, then it's always green. So it means methane is effectively being removed. But for low emissions of iron or chlorine, we see that you can also be in a regime that is here, has a red color. And that means that methane is going up. So it's that same effect that I showed before, where there's this up and down effect. What we saw is that depends on how polluted the air is. If it's highly polluted, then it's always fine. Then methane is always removed. If it's very pristine air, it works well. But if it's in between, then it's really sensitive to how intense the emission is. And we made a world map here that shows you basically the color of is it positive or in a negative place of the planet. And what you see is most of the world is in this in-between region, which means that this idea of adding iron in ship plumes might not work so well. And the reason for that is that you can see that on this graph, where when a ship emits a plume of, for example, iron particles, then close to the ship, it's going to be a highly intense emission because it's all still together. But then the plume will disperse and concentrations go down. That's what you see in this graph. It starts with a very high chlorine emission due to the iron, that is added, and then it disperses, so it goes down and can then enter that less favorable regime. And that's the problem because, if these particles stay in the air for multiple days, but after a few hours you already enter this unfavorable regime, then these iron particles are spending most of their time, not being very effective or having the counter effect that you want. So ideally, looking at it like this, you would want these kind of particles, but then you want them to basically neutralize after a few hours, because then you could really use that benefit of high intense emissions close to the ship. And what's more, ship plumes are highly polluted. So because it's coming straight from a shipping engine, so it's also in this highly polluted regime that's also beneficial for removal. So in those first few hours, that's when it's positive. And ideally, you want a particle to also only work in those first few hours. And that's the particle that we found, and that's the topic of the CIEIF project that we're doing. So we discovered a family of short-lived ISA-type particles. And we will be publishing this in a scientific publication in the coming months. And that particle is similar to the iron that I was just talking about. So it recycles the acids, and it uses sunlight, and then makes chlorine, and that destroys the methane. But the big difference is that these particles, they neutralize, they become inert after 1 or 2 hours after the emission. And that's nice because it means the impact of the ship plume of this emission is localized. So here you see on the right a plume dispersion model result, and the green part here is the first hour after emitting the ship plume, and it shows that if you take 1 hour, then maybe it's 5 or 10 kilometers downstream of the ship. That's how far the impact will go. And that makes it easier to assess the environmental impact, which is also what we're going to do in this CIEIF project, to try and assess the environmental impact of such an intervention. So we call this a plume-based reactor because we're taking advantage of these first 2 hours that have ideal conditions, and we can also do it in a place that's also under control. And possible application for this could be to use this to reduce the methane emissions from LNG engines on ships. They leak methane, and you could maybe use these particles for the mitigation of those methane leaks. So that's the topic of our study as well. And that will create some financial sustainability too, in principle, because ships need to pay fines for these emissions. So it's worth money to also reduce these. Now, the CIEIF project is therefore, what we're going to do in this project is dispersion modeling and an environmental impact feasibility study. So we defined a hypothetical field test, so not a real test, but a hypothetical one in the North Sea in the Netherlands, where we then hypothetically emit this particle in a ship plume, and then it is enough of the particles to also compensate for the methane leak from an LNG engine. And then we study what could be the environmental impact of this. So there are some anticipated technical environmental impact challenges that we investigate. One is air quality challenges. We want to know if there's increased particle formation, and what are the secondary pollutants that we can expect. We want to look at ocean water deposition of these particles. What is the impact of that? Also, fugitive CO2 emissions, because the chlorine gas is a gas that needs to stay within safe levels, and the impact on higher marine life. So think about birds and fish. Now, this new particle, we think it has some advantages that we want to study. One of them is a delayed chlorine release. And it's because that particle takes time to convert and generate the chlorine. It means it creates the chlorine as it's downstream of the ship itself. And we think that helps to keep it within safe levels close to the ship. It also has that same benefit of recycling the acids, so that it doesn't increase the acidity of the environment. So we want to confirm that too. And we believe and want to know if that residue from this particle has a low impact. And the way how we do this project is that the dispersion modeling will be done by ourselves, which we provide as input to an independent consultancy. And that consultancy then does the environmental impact feasibility assessment. And that's it for my presentation. Thank you very much. And ready for questions.
All right. Thank you so much, Peter and Maarten. And yeah, so we will move on to questions now. And again, I encourage everybody in attendance to populate the Q&A box with any questions you might have. But I'll kick it off with a couple of questions. I'm going to start with Peter. I was wondering if you could tell me what your rationale was to limit the scope of what you're funding, right? To largely EIA and modeling. What was your thinking when you were originally creating the fund?
Well, there are plenty of other funds giving larger amounts of money for, basic implementation and research. We didn't want to compete in that field. We wanted to fund in the area in which we have expertise, which is EIA and stakeholder outreach, so that, we could constructively engage with our recipients on those topics. And as I said at the beginning, we really saw that as sort of an unmet need for those proposing field tests, across these various technologies where, they may have achieved some funding to do some basic implementation or to do some research, but they lacked, enough money to reach out and do the EIA work that is essential, we think, for, getting permits and moving such field tests ahead. So it's a pretty applied, focused, narrow area where we're trying to help.
Great. All right. Maarten, I want to turn to this approach you're talking about, and just ask you a few questions about it. Now, obviously, one of the things that you're doing with this funding is to look at ecosystem or potential ecosystem impacts, right? And you suggested what some of those impacts could be with some of these other approaches that you outlined prior to this. I'm wondering if you could provide a sense of what potential impacts you're likely to see and are seeking to assess in this context.
Yeah, and thanks, Will. How we made the list of anticipated challenges is by looking at the research that has been done on these other approaches. So, for example, one of the things that in the past year was found is the potential of secondary aerosol formation, because the enhanced oxidation can cause more particles to be formed. So that's, for example, one topic that we then want to look at. We ourselves found the acidity as an issue for chlorine emissions, and it should be that this is solved in this particular version, but that's then something that you definitely want to look at. The other way how we looked at it is, and this is also maybe something to say about CIEIF as well, is that within this review process that we had with CIEIF, we got some really good feedback also from their reviewers, and that information also helped us to sharpen what are the anticipated challenges that we want to look at. So, for example, birds is something we had on our radar, but we had a lot of discussions about the potential impacts on birds and how you should study that. So that's also a way how we identified some additional things that we wanted to look at that we didn't think about beforehand. So yeah, I think that's something positive about this fund also, that when you apply, it is some really expert people that give feedback. So that's also a positive thing.
Great, thanks. So another question. It's probably an unfair question at the stage that you're at in terms of the research, but do you have any sense of what the potential amount of methane removal might be effectuated at scale, assuming this approach is, successful in terms of initial field trials?
Yeah, so there's two ways to look at that question, because one way to look at it is how much is needed,
Right.
and the other way to look at it is how much is possible. So how much is needed was studied by Chris Smith from EASA, and they studied how much methane removal is needed to keep the planet below 1.5 degrees, and that's a lot. So and that is close to this 200 million tons of methane removal. That is also in the IPCC scenarios. in the case Chris Smith, he has even a graph. It shows how much each year, because assuming that things like CO2 emission reduction, etc., and also methane emission reduction progresses, you need a lot for a certain time, and then you don't need it anymore. So that's one way to answer, and that's if you convert this to chlorine, that's a lot of chlorine emissions, and that's like 1,000 gigagrams or so
Right.
per year. So huge amounts. How much is possible? That's hard to tell. So yeah, it's because this field is in its infancy. So we're really at the
Hmm.
beginning of this type of research. And I already know that this idea with these plume reactors, I don't think that can scale to this 200 million ton of methane. This is, but yeah, I think a good answer is also by Abernethy. He studied when does it become beneficial or useful to study this stuff, and he puts the threshold at around 1 million ton per year. So if you're able to
Hmm.
reduce 1 million ton per year, you're making an impact that is useful. So I think that would be a good number to strive for initially, and then scale from there where possible. And it all depends on environmental impacts and but also a governance, a global governance that even makes it possible at all if at these grand scales. Otherwise, it will probably stay relatively small.
Okay. Um, Again, probably an unfair question at this stage, but it, ones that is a big concern, obviously, in carbon removal are costs, right? Any sense of what the cost of this would be toward in terms of the pertinent units that you're looking at?
Yeah, that's a question we get a lot, and also we did some calculations there. And some others did calculations. So a group, Yuan, published this year a paper about chlorine, so making chlorine gas with electrolyzers and using that. And they got to a very low cost. So a cost could be below 200 or even below $100 per ton CO2. So that's really a low cost if you compare that with the direct air capture type of costs that are
Hmm.
there right now, even if that would be at scale. And so this methane removal could with chlorine could happen at lower costs and at smaller scale already. So we also did our own calculations for this new particle, and it's in that same ballpark uh, of below $100 per ton that we think this would cost. So cost-wise, it seems feasible also in view of the value that methane removal has economically.
Hmm. Could the one of the things that you talked about was the potential for methane pollution remediation. Also, would that potentially be another substantial value proposition for this approach in the longer term?
Yeah, what do you? I'd like to also kick this one back to you, Bill, because I'm curious what you think. Because this, my thinking is that it's better to start with emission reduction because that needs to
Hmm.
happen first. So if you could use this technology in reducing emissions that are happening now, I think that's a good place to start. But yeah, how do you look at it? And is there maybe some analogy from CO2 capture?
Yeah, I mean, I think that's a reasonable proposition. It will be helpful if it can produce some kinds of co-benefits, right, that help pay for it, right, as you suggested are possible. Um, I guess some of the research will help bear that out, hopefully. So it's so I'm gonna move to audience questions now. First question, yeah, you alluded a bit to governance questions, right? And I was trying not to jump into that too much because I'd get excited and take all the time. But somebody's asked one, so we'll look at that here. The question is. Um, could you have a global impact on methane removal and reduction by solely working within the 200-mile exclusive economic zone of coastal nations, at least initially? And the rationale was, as probably a lot of people know, is there's a new treaty that just entered into force a couple of days ago called the Biodiversity Beyond National Jurisdiction Treaty, right? Which is a treaty under the Law of the Sea Convention that seeks to enhance protection of biodiversity in the open oceans, right? And the treaty, how the treaty is operationalized, how it's fleshed out, right, is largely going to be determined by what the parties do. It's a very organic sort of process. But the questioner was suggesting that it may have pertinence for regulating something like methane removal, at least in the open oceans. So could you do this within EEZs and have a real impact? And I guess the allied question of it is that the BBNJ says that if you're doing something within your EEZ that has impacts on the open oceans, you could still be subject to the treaty. So I guess that's a two-part question. Could you do it within EEZs and get any bang for your buck? And would it still have exogenous impacts beyond EEZs if done at scale?
The two of you might be better suited at answering the policy questions, of course. But from a technical point of view, we would need to do the same type of modeling that I presented, where we had modeled chlorine release from the oceans. But then we would need to do it with releasing the chlorine from only coastal regions and see if that how scalable that is. So it's a nice question that we would need to model. At least it's with a plume reactor, it's possible to stay within the economic zone because it's only 5 or 10 kilometers big. So you can stay within it. That's possible. How scalable it is, that needs to be modeled then.
Right. The second part of that question, even if you could do that, right, or you can do that, it sounds like, but if you did that, would it still potentially have exogenous impacts beyond the exclusive economic zone?
Oh, yeah. Of course, if you destroy methane at a large scale, you
Right.
remove it all over the planet. So the
Right.
benefits
Right.
go across the planet, but I
Right.
don't know if that's a problem.
Yeah, yeah, yeah. Yeah, I think that's from a policy standpoint an interesting question because under BB&J, as I said, I think people often think, well, if it's not being done in the open ocean, it's not subject to its jurisdiction, but it has this provision that says if you're doing it within your EEZ and it has an impact beyond that, you still could be subject to some of its mandates. So that's I think an interesting policy question. So thanks for that one. Next question. Is there any concern that some chlorine ions will reach the stratosphere and destroy ozone?
Yeah, that's a question that also comes back sometimes, and a few researchers have studied it, including us, with this one study. So let's say the jury is still out for what the modelers are finding, but there's also you can look at it from a chemistry point of view. The product that you get when chlorine destroys methane is hydrochloric acid, HCl. And that has an ozone depleting potential of 0. So
Right.
hydrochloric acid, it doesn't go to the stratosphere because it's taken up by rain, and it rains down. It doesn't get high enough. So for this to go to the stratosphere, you need a different type of molecule like CH3Cl, and some of that is formed, but not much. So that's a really small effect. But at the same time, we're seeing that in our modeling that the chlorine in the stratosphere goes up. Why do we see that? That's because methane itself has a limiting effect on how damaging the chlorine is. So the chlorine that's out there from previous CFCs and etc. It becomes active, and when it reacts with methane, it becomes that hydrochloric acid again. That neutralizes it for a while, and it slows down the ozone destruction. So when you have less methane, you also have less of the methane helping to slow that stuff down. So that's why you're going to see an increased chlorine, active chlorine in the stratosphere. But it's for a different reason. It's not like for traveling from below to up, but it's more related to methane itself that is lower. And so it's a complex story of how the ozone is destroyed, and is this now a good thing or a bad thing? Yeah.
Right. Okay. All right. I think we have time for one last question. So, question is, can these methane removal technologies scale up fast in case of a methane burst, for example, from a rapid thawing permafrost, right? It's one of the nightmare scenarios, right, that we add on to all the other nightmare scenarios associated with climate change.
I would say not yet
Yeah.
because it's an emerging field, so it's really at an early stage. So yeah, can't even say yet if it definitely works, right? So it's too early to tell. I think if it can do things at such a tremendous scale, I don't know.
A question related to that, kind of from a logistical perspective, right? You said, like, obviously, fair enough, foundationally, you have to determine if this even works at that stage in field experiments. Assuming it did, and you wanted to do this at scale, what would this look like logistically?
Yeah,
What would you
so
need to do to do this on a really large scale?
yeah, yeah. If you go for the paper presented by Yuan, where they
Hmm.
where they took electrolyzers and they make chlorine with that.
Hmm.
So to scale that up to the level that you need, yeah. So how many electricity power and electrolyzers do you need? I think that's feasible. So I did a calculation that if the European Union would want to achieve its 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 um, its commitment for methane reduction, that's 30% reduction, it needs two very big offshore wind turbine parks with electrolyzers that they
Hmm.
actually are already building for hydrogen production. So maybe 20 gigawatts of electricity, and if they would use this chlorine machine, then it would be enough chlorine to reach their goals. But of course, let's study the environmental impacts first before considering a thing like that.
Hmm. So would this ultimately would one of the concerns about this ultimately be the amount of energy that would be required to effectuate these goals?
I don't understand the question.
Oh, you're talking about one of the concerns that we have with some of the electrochemical approaches in the context of carbon removal, like ocean alkalinity enhancement, for example, are the energy requirements. Would that ultimately be one of the potential challenges associated with this approach?
Maybe, yeah, at least according to this paper I'm quoting,
Yeah,
then
that's like a big
their
number.
electricity is the main input that they need for that one. But this is just what I'm telling you is just what from literature, what's out there. So, but I can provide also the references if people are interested in that.
All right, that's great. Okay, we have reached the top of the clock, and so I would like to thank Peter and Martin for a very interesting discussion, both in terms of the grant program, which I encourage anyone that's working in the field of climate intervention to take a look at. Uh, Almost any time you're doing these, there's going to be a need for modeling, there's going to be a need for environmental impact assessment, and I think this is a nice um, uh, uh, well-focused source of funding for that. And I'd like to thank Martin for talking about another form of climate intervention that we're definitely going to continue to be discussing in this world. So, and I'd like to thank again everyone who's joined us. Uh, Please come back in a couple of days. We'll have another webinar on this Thursday, and we hope you can join us then also. And so with that, I will say goodbye now.
Okay, thanks a lot, everyone.